All right, let's look at this method of integration by parts. I'm sure some of you may remember that when we were doing differentiation, we could have a scenario where we had two functions multiplying each other. And the case that is particularly of importance to us in here is when you have these two functions being different types of functions. You know, we normally summarize the types of functions by using the word Lipet. Lipet tells you the types of functions that we have. The L is for logarithmic functions, okay? So this is for logarithmic functions, and an example of a logarithmic function of a logarithmic function is a function that has ln or lg or log. You know, log, if we just say log, we normally mean base 10, right? lg. ln is log base e. And it could have anything, yeah. With these logarithmic functions, and then here, the second one would be for inverse trig. Inverse trig functions to say sine inverse of x, okay? And all those other examples. Or we could have this is polynomial, which is the basic algebraic functions, okay? Polynomial function. Or, for example, we have t, we have x squared, we have theta, 3 theta or something. These are all algebraic because what we just have is a symbol representing something that we could differentiate there or integrate, right? The variable theta would be representing something we don't know, and x and t, okay? Now, e here would be for exponential functions, okay? Exponential functions are, for example, e to the x, right? These are in exponential. Then we have the normal trig functions, okay? The trigonometric functions. For example, sine of x, tan of x, right? So here these are some of the types of functions. So now you can have a situation where you have a function of one of these multiplying with the function of another one that's part of these. Like I can take a logarithmic function multiplying a polynomial. I can take a polynomial multiplying an inverse trig. I can take a polynomial multiplying an exponential. All that, right? So here, this u is a function of x, and v is a function of x, okay? But there might be, one might be a log function, the other one a polynomial or whatever, right? If I have them doing that, if I have them multiplying, for example, they ask you to find the integral of x squared cos x with respect to x. Here you have a polynomial function in x squared, and you have a trigonometric function in cos x. How would you do that? How would you integrate a product of two functions? This is when we use the method of integration by parts. And we'll look at it in the cases. Here we just want to see what it looks like, what this method of integration by parts looks like and where it comes from. Well, here is what it is. If you remember the product rule of differentiation, what we had was the derivative. We have two functions, u, v, which are both functions of x. And we want to find the derivative of them. They are multiplying one another. We want to find the derivative of that. Well, we would say differentiate the first, which is u, then multiply with the second as it is. So it would be v du dx plus, you now differentiate the second one, it is dv dx now. Then you multiply by the first term, which is u, okay? So what did we do? We differentiated the first multiplying by the second, then we differentiated the second multiplying by the first. We add them together. This is the product rule of differentiation. That's how you differentiate if two different functions are multiplying. Now, when we integrate, we come from here. We come from this idea. What do? We make u dv dx the subject of the formula. Okay? And that would mean we take this v du dx to the other side. So I now have d dx of uv minus v du dx being equal to u dv dx. It's positive, so it stays positive, right? And we can like turn around the fraction, not the equation. Nothing changes. So like if I say 5 equal to 7, let me say 5 equal to 7 minus 2. Then I flip it, I say 7 minus 2 equal to 5. I've just flipped it, writing it the same way it was. So if I flip, I would be saying u dv dx, okay, is equal to d dx of uv minus v du dx. So I haven't changed anything. The minus is still on this guy, and this guy is still positive. Right, I've just rewritten it. Now, okay, from here, we take the integral of everything here with respect to x. So it would be integral of u dv dx. And you know integral has to be with respect to something, so we are taking with respect to x, is equal to the integral of d dx of uv, this is the integral with respect to x, minus the integral of v du dx with respect to x. All right, now if I'm taking, and here, all you just have to do is, we know that in this section, if I rewrite this one, it will be the integral of u dv dx with respect to x being equal to, this is the derivative of uv, so d dx of uv, then the integral of uv, of that derivative. So if I differentiate, I go one way. If I integrate, I'm coming back. It's like anti-differentiation. So here, I differentiated uv, then I integrated my derivative. So I'll be back to uv. Minus integral of v du dx with respect to x. Now this is brought down to the integral of u dv. It's like the dx and the dx cancel, okay? But in literal sense, it's not what happens, but it's like that happens, okay? uv minus the integral of v du, okay? So I have to be now with respect to u. That's what you must know. So this is just like what it is. So this is what we'll be having as our integration by parts formula. Okay? We have two things that are, we are integrating x squared cos x with respect to x. All we are going to do is, we know that we must make one to be u and the other to be dv. So we are going to see the rules now where we choose one to be u, and then the other one, automatically, the cos x, would then be the dv. And then we know that we will now need u we will need v. And v, after having him, we will also need du. So in other words, we would have to integrate this dv to get v, and differentiate this u to get du. Then we just plug them into this formula, and then we can be able to find our solution. Okay, so first would be to identify the u and the dv. Then we can now differentiate the u to get du and integrate the dv to get v. Then we plug them into this formula, then we can be able to use that. Okay, so it's not a hard method. All you must be good at is, you must be good at the derivatives and the integrals of all these types of functions. How do you differentiate a polynomial function? How do you integrate a polynomial function? How do you differentiate an exponential function? And how do you integrate it? This would be handy. Even for a trig function, it would be handy in this method. All right? Bye for now. See you in the next video.